The Slinky. Invented by accident in 1943, it's been entertaining people of all ages ever since. This is probably due to some of its unique qualities, such as its ability to so gracefully descend stairs, or the way that it seems to hover in midair when dropped. This phenomenon is what we're going to be exploring today. Now, I'm sure that you've all seen a Slinky drop before, but before we dive into the physics, let's take another look at it. Slinky is basically just a giant spring, so that's how we're going to model it. Let us compare the forces at 3 different points along the spring: the top, the middle, and the bottom. We're assuming equal distribution of mass, so all of the gravitational forces should be equal. The differences are apparent when we look at their spring forces. The top point has 1 spring force in the negative y direction. The middle one has 2 spring forces, 1 upwards and 1 downwards, and the bottom one has 1 upward spring force. So this is the picture of the Slinky that we have when it's suspended. So now let's take a look at what happens when we drop it. When the Slinky is dropped, the top points quickly accelerate downward and compress, while the bottom remains apparently stationary. If we look at our 3 points from before, we can see a change in their forces. While gravity is still acting on all of them, the spring force on each has changed. As you can see, our top point no longer experiences any spring force, our middle point experiences only a downwards force, and our bottom point experiences an upwards force as before. The only thing that's changed here is the magnitude of this spring force has decreased slightly as the top coils have compressed. But as long as it's equal to the gravitational force, the bottom here will continue to hover.
By viewing the simulation, we can see the forces change as the Slinky expands and then falls. The red arrow represents the force of gravity acting on the bottom mass, while the blue arrow represents the spring force on the same mass. Notice how the blue arrow grows to the same magnitude as the red arrow and results in a system at equilibrium. When the Slinky is dropped, the blue arrow begins to shrink. Once it is significantly smaller than the red arrow, the bottom point starts to fall.
So now we're going to take a look at the way that a falling Slinky behaves like a wave. As the upper coils begin to collapse on one another, they form a compression wave that will then travel down the entire length of the Slinky. This wave has a period that goes as the square root of m over k, where m is the mass of the Slinky and k is the spring constant. So now we're going to take a look at a couple graphs, the data of which is from the program that you just saw, and we're going to show that this is true.
So we want to show that the period of the compression wave goes as the square root of m over k. To do this, we will vary m while keeping k constant so that the period should go as the square root of m times a constant. By taking the log of both sides, we have a function in the form of y equals a times x, where the slope, a, is the exponent. So for our case, the slope of our graph should be 1/2. This graph was created using the program from earlier in the video by measuring the time it took for a certain portion of the Slinky to compress. As you can see, the slope is very nearly 0.5. The fact that it is not exactly 0.5 is most likely due to the fact that the program is an approximation, and it is possible that the code wasn't as precise as it could have been. However, this graph still clearly demonstrates that the period does in fact go as the square root of m over k.
So while a Slinky may be a simple toy, it has applicable properties to other systems in the physical world. This includes a falling rod. You've probably seen videos where a rod falls, hits the ground, and then pops back up. This motion is due to a compression wave. As the rod falls and hits the ground, the atoms at the bottom can no longer go anywhere, so they start to compress against one another, while the atoms at the top are still accelerating downward. Eventually, these atoms fully compress. So this wave travels all the way up and compresses them all together. Once they're all compressed, this spring, it has a lot of tension and wants to release, causing the popping up motion. So while Slinkies may not have very many scientific applications at the moment, their properties can be used to study other systems that we can't necessarily study as easily. Well guys, I hope you enjoyed the video and I hope you learned a little something about the Slinky. Thanks for watching.